Hello, welcome back to Learn Physics. In today's topic, we are going to discuss about nuclei. Okay, in the previous videos of class 12, I did for atoms and the one numerical portion also we did, isn't it? So in atoms, we already learned about Rutherford's atom model and Bohr's atom model. There and all we learned that it has most of the mass of an atom is concentrated at the center, isn't it? Most of the mass of the atom is concentrated at the center, and it is at the nucleus. Okay, so here we are going to study about this nuclei. Okay, the nucleus, what and all are there in the nuclei, all those things, and what will be the mass of nuclei, and the rest of the things we will be studying in this chapter. Okay, so first one is nuclei. In nuclei, first we are going to study about the atomic mass. So what is meant by this atomic mass? What is the mass of an atom? Mass of one atom is 1/12 of mass of carbon 12 atom. So that is one atomic mass. One atomic mass is 1/12 of mass of carbon 12 atom. So one atomic mass, I'll be representing it as 1U. 1U equals 1/12 of mass of carbon 12 atom. So 1/12 into, what is mass of carbon 12 atom? Yes, 12 divided by Avogadro number. So while cancelling this one, we will get it as this 1.66 into 10 to the power minus 27. Like that we will get kilogram. Okay, so this is the mass of one atomic mass unit. So if we are representing any mass of one atom, we will be representing in the order of this one. So this will be considered as, so we will be always representing the mass of an atom in terms of an integral multiple of mass of hydrogen atom. So first we will consider the mass of hydrogen atom, that into 5 times, 6 times, so it will be an integral multiple of mass of hydrogen atom. Okay, clear? So this is how we will be finding out the atomic mass. Okay, so the next one is about the nucleus. Okay, so when we are considering about the nucleus, we already told nucleus has positive charge. That is why when alpha particles are coming near to the nucleus, alpha particles are coming to the gold foil at a particular distance. After a distance of closest approach, it will start repelling, isn't it? Potential energy, the kinetic energy is converting to potential energy, we told. So that distance is called, so in this area it has positive charge. It has positive charge in this. Okay, so the nucleus has a positive charge. So inside the nucleus, what is there? It has protons. Initially we were knowing only about the protons. Protons means we will consider it as hydrogen. Hydrogen has different kind of isotopes. Okay, so hydrogen it consists of mainly the nucleus consists of protons. The nucleus consists of protons. Okay, the nucleus has protons inside that. That nucleus consists of only protons. But when the scientist named Chadwick, when he was doing some experiments relating with beryllium is bombarding with alpha particles, when he was doing that experiment, he understood that some chargeless particles are coming out. Okay, so the chargeless particles are coming out, like that he understood. He understood that some chargeless particles are coming out. That means it is radiating some chargeless particles. So at that time, the chargeless particles known to us was only about the photons. Okay, so he thought that it was photons. Okay, but when we were considering about the energy, conservation of energy, when he was considering conservation of energy and conservation of momentum, he understood that that is not satisfying the photons, properties of photons. So he understood that the nucleus consists of another chargeless particle called a, yes, he named it as neutron. So he understood that particle is named it as some another chargeless particle is there inside the nucleus apart from this protons. Okay, so nucleus consists of another chargeless particle called a neutrons. Like that, who understood? Chadwick understood. From which experiment? When he was doing some experiment relating with a beryllium bombarding with alpha particle, he understood that some chargeless radiations are coming out. These radiations are chargeless. So initially it was at that time only chargeless particle which we know was photons. So he thought it will be photons. But when he was comparing it with the conservation of energy and momentum, it was not at all. He understood that this is not photons. So another charged particle. So he had given the name it as neutron. For this discovery of neutrons, he got Nobel Prize afterwards. Okay, so this is how the nucleus consists of protons and neutrons. So now you got an idea about atom. Atom means it has center, it has nucleus. Nucleus consists of protons and neutrons, and away from the and outside the nucleus, electrons will be revolving in an orbit. Okay, so this is about the nucleus. Okay, so in here, while we are considering an atom, so how we can represent an atom, what and all will be there inside the atom, that and all we are going to study now. Okay, we are going to study how we will be representing an atom. Okay, so if X is an atom and we will be representing it as ZA. This is the representation of an atom. Okay, an element we will be representing like this, X, Z, A. What is this Z? Z is called an atomic number. Z is the atomic number and A is the mass number. Okay, atomic number means it is the number of protons present inside it. Okay, mass number is number of protons plus number of neutrons. So this is called a mass number. Mass number is the number of protons plus number of neutrons, and here atomic number is the number of protons. We know, suppose if Z is the number of protons inside a nucleus, then plus Ze will be the total charge of the nucleus. Nucleus will be having plus Ze charge. For an atom, it will be neutral in nature. Atom will be neutral in nature. It has plus Ze charge, means it will be having that many number of electrons also. So because it should be neutral in charge, isn't it? Z number of protons are there, means Z number of neutrons also will be there to in order to become the atom as neutral. Okay, so to make the atom neutral, so that is how the atom is becoming neutral in nature. How many number of protons are there? That many number of electrons will be revolving around the nucleus. So inside the nucleus, number of protons is represented as Z, and mass number means total number of protons and number of neutrons. Together we will call it as mass number. So if we need to find out the number of neutrons present, how we can find out the number of neutrons? Z minus A, because this is the sum and this is the number of protons. So if we need the number of neutrons, Z minus A will give you the number of neutrons present. And remember that neutrons doesn't have any charge, it is chargeless. Okay, clear now? So next we are going to study about isotopes, isobars and isotones. What is meant by isotopes? Isotopes are the atoms of an element which have the same atomic number but different mass number. I told you how we will be representing an atom XZA. This will be the representation, isn't it? So Z is the atomic number and A is the mass number. So in an isotope we can see same amount of atomic number, different amount of mass number. That means Z is same, A is different. So what will be different over there? Yes, neutrons will be different over there. Number of neutrons will be different in isotopes. See here, for hydrogen atom, if we are hydrogen atom, while we are considering 1H2, 1H1, 1H2, 1H3. These are the isotopes: protium, deuterium, tritium. So here, if I am considering, what will be the Z over here? 1. Here Z is 1. Here also Z is 1. But what about the A here? A is, what is 1 here, and A is 2 here, and A is 3 here. What will be the number of neutrons here? XZA. So yes, A minus Z. A minus Z is the number of neutrons. So it is 0. Here number of neutrons is 1. Here number of neutrons is 2. So number of neutrons will be differing in isotopes. Okay. So next is isobars. Isobars means it has the same mass number but different atomic number. Atomic number will be different. So if you are remembering one example, it will be easy for you. So here, what is this one? Same atomic number, different mass number. Here same mass number but different atomic number. Okay. So if atomic number is same, then we can say isotope. If mass number is same, then we can say it is isobars. So here tell me, what is Z? 11. And here Z is 10. And A is 22. Here also A is 22. Okay, here while we are calculating the neutrons, number of neutrons, how much we will be getting? We will be getting it as 11, and here we will be getting it as 12. Okay, so it consists of different number of protons and different number of neutrons, but the total, the sum will remains the same. Okay, so that is isobars. Next is isotones. Isotones means same number of neutrons will be there. Okay, so neutrons will be same. So here Z equals 1 and next Z equals 2. But here A equals 3 and A equals 4. What is the difference? 2 and this also 2. Neutrons will be same here, but both will be different. Atomic number and mass number will be different. So here isotope means same atomic number. Isobars means same mass number. Here isotones means same neutrons, same number of neutrons. So clear this one, isotope, and at least one example you should know. Okay, only in the case of isotones, number of neutrons will be same. Okay, same atomic number is this isotope and same mass number is isobars. Okay, clear this one. So next we are going to study about size of nucleus. Size of nucleus means the radius of the nucleus is directly proportional to the 1/3 of mass number. Okay, so 1/3 of mass number. So R equals R0 into 8 to the power 1/3. R0 is 1.2 into 10 to the power minus 15 meter. So this is R0. So R equals R0 into 8 to the power 1/3. So the volume, how it will be depending on, we know 4/3 pi R cube is the formula, isn't it? So while we are calculating this one, volume will be R0 8 to the power 1/3 the whole power 3. So it will be depending on volume is directly proportional to the this mass number. Okay, so R is proportional to the 1 by third of the mass number of the nucleus. Okay, so we know this R0 is an empirical value, that is 1.2 into 10 to the power minus 15 meter. So this is how we will be finding. This is an important one. This can be asked for a 1 mark 2 marker question. Many times it is asked. So remember this equation. R is proportional to the A to the power 1 by 3. Okay, clear? So next we are going to study about the mass energy equation. So next is mass energy equation. Usually most of the children will be knowing this equation. If Einstein's picture is there, next to that equation also will be there. What is that mass energy equation? Yes, E equals mc square, isn't it? So E equals mc square as the mass energy equation. This equation most of you will be knowing. So but what is this equation? Through this equation, Einstein is telling like, see, this mass we can convert to energy. Okay, that is mass energy equation. We can convert the mass into energy. How we can convert the mass into energy? That is the importance of this mass energy equation. Through mass energy equation, we can convert mass into energy. Can we convert the mass into energy? In the nucleus, in the energy of the nucleus, we can very beautifully show mass can be converted to energy. So here, see, mass of protons are there, mass of what is the energy of the energy of the nucleus? Energy of the nucleus also will be depending on the mass of this protons and neutrons. Okay, so if we are thinking like if the number of protons are increasing, members are increasing, the energy also is increasing, isn't it? So here in that way, it's very normal way if we are thinking also, that will be the reason. Okay, so here mass energy equation, mass we can convert to energy. How we can do that? So all the nucleons are bound to the nucleus, isn't it? All the protons, nucleus, everything is tightly bound to the nucleus. So that energy required for the electrons for the nucleons means what and all are there inside the nucleus? Protons and neutrons are there inside the nucleus. So the energy required for those nucleons to bind inside the nucleus, to be there inside the nucleus itself, it requires some energy. So that energy is known as binding energy. So if it needs to come out from the nucleus, it should release that much of energy and come out from the nucleus. So the minimum energy, the energy required by the nucleons inside the nucleus is called as binding energy. Okay, like these nucleons are bound to the nucleus with this much of energy. Okay, so how we will be finding out this binding energy? So if we are calculating the binding energy, so you just think what will be the binding energy. We know the mass energy equation. What is the total mass of the nucleus? So into c square will give you the binding energy. Nucleus means it consists of protons and neutrons. So what will be the mass of nucleus? Mass of nucleus will be equal to mass of protons plus mass of neutrons, x, z, a, isn't it? So how many number of protons will be there? Z into mp. Okay, how many number of neutrons are there? A minus z into mass of neutron. This will be the total mass of the nucleus. So while we are calculating using mass spectrometer, okay, we can find out the mass of a nucleus, okay, or mass of an atom we can find out with the help of mass spectrometer. So while we are finding out using mass spectrometer, we will be getting one mass, and while we are calculating like this, we will be getting another mass having a slight variation will be there. Okay, so what will be the difference which we are getting through these two methods? That is called as mass defect. Okay, there is a defect in mass. So there is a defect in mass. Now we are going to calculate what is the defect in mass or change in mass. So this is the original mass which we got from the theoretical way, isn't it? A minus Z into mass of neutron, that into C square, isn't it? If using mass spectrometer, if I am finding out the mass of a atom, I am getting like this. M is the mass of the atom using mass spectrometer. So while we are taking the difference between these two, so first suppose if I am getting one value for this one, that one minus using mass spectrometer, how much we got, that is called a mass defect. Okay, this mass defect into C square will give you, so this is the, so here energy is not required because this is energy. So mass is mass, total mass is this much, and mass using spectrometer is this much. So this is the mass defect. So mass defect into C square will give you binding energy. So what is the, so because here while we are calculating, we are getting the total mass by theoretical method. That should be the total mass of the atom. Okay, so while you are using the mass spectrometer, that is practical method, we are getting the mass like this. Okay, so there is a difference. What is that difference? That difference is due to the binding energy. So what will be the binding energy? That mass defect into C square will give you the binding energy of the nucleus. Okay, so this will be the mass defect into C square will give you the binding energy. Okay, so understood if how we will be calculating the mass defect and all. So nucleus consists of protons and neutrons. So mass of a nucleus will be equal to mass of proton plus mass of neutron, or mass of an atom we can consider like this. Mass will be equal to mass of proton plus mass of neutron. Okay, Z into mass of proton plus A minus Z into mass of neutron. Okay, so delta M will be equal to this much. This capital M is the mass we found out using your spectrometer, isn't it? Delta M into C square will give you the binding energy of the nucleus. Okay, so this is the binding energy of the nucleus. Okay, so this is the binding energy per binding energy of a nucleus. So we are getting, so here we are finding out for the binding energy of a nucleus, the total mass of the nucleus using spectrograph, and we will be getting delta M into C square equals binding energy of the nucleus we are finding out. Okay, so next we are going to study about binding energy per nucleon. Okay, so here total binding energy per nucleon. That means binding energy divided by A. What is A? A is the mass number, that is binding energy per nucleon we are going to find out. Okay, so if we are drawing a graph for binding energy per nucleon and mass number. Okay, if we are finding out the graph between binding energy of per nucleon and this mass number, we will get a graph like see, while we are taking the value from 30 to 170. Okay, from 30, this is represented in mega electron volt. Okay, from 30 to 170 it will be almost same, and after that, before that it will be decreasing, all those values will be, and afterwards see it is from 30 to 170, that is atomic number is between 30 and 170. Okay, including 30 and 170 it is almost constant. So that heavier nucleus are having less binding energy in mega electron volt, and lighter nucleus also will be having less binding energy. Okay, so heavier nucleus and lighter nucleus are having lesser binding energy. So if the two atoms are joining together and fusing together and forming a nuclear fusion. So in the case of nuclear fusion, what will happen? See, nuclear fusion means smaller atoms will combine together to form a heavier nucleus, isn't it? So if these smaller atoms are combining and forming a heavier nucleus below this 170, it will be releasing a greater amount of energy because of this. See, it has, yes, so because of that it has larger amount of energy, so it will be releasing that much amount of energy over there. The same way, if in the case of nuclear fission, if I am considering nuclear fission, heavier atoms will be splitting and forming the lighter nuclei. So these heavier atoms splitting and will be forming the lighter nucleus in this range, then it will be again releasing a large amount of energy because of this binding energy. Because of this binding energy only, it is releasing more amount of energy. Okay, so clear now. This is what is this thing. Actually, the last year one question had come from this portion. Okay, so what are the binding energy per nucleon curve and mass number? How we will be representing the graph? So the graph will be, so this decreasing, increasing. So here if I am using an element having this atomic number and will be using will be trying to see from higher to lower I can't make. Okay, always from lower to higher binding energy only we will be getting enough amount of energy. So that is why we can't use all the elements for nuclear fission and fusion, isn't it? So the elements which are combining together and forming a heavier nucleus means binding energy we should consider. After considering the binding, in which way we should consider? The output should have a greater binding energy, then only the release of energy also will be more. Okay, clear? So this is an introduction for your this nuclei. So I hope all of you understood all those things. If you like the channel, please don't forget to subscribe. Just keep on watching, learn physics. Thank you.